This is page 8 of the fault tolerance notes. And section 2.4 is the convergence algorithm, or CMV algorithm. And the text reference for this is 13.4.4.2. So if you find this confusing, I'd suggest checking out that reference. This is an example of a distributed clock synchronization algorithm. And it was developed by a prof, I think they're at MIT, named Leslie Lamport. And Leslie Lamport did a lot of important work in distributed systems. He also developed, well, he built on a document formatting system. So there was a document formatting system called TeX, that's T-E-X, developed by Donald Knuth, who's like one of the pioneers in computer science. He was a prof at Stanford, I believe he's still alive. He came up with a volume, or a couple volumes on proofs and runtime complexity, that kind of stuff. And he actually visited Waterloo. So my mother-in-law got her BA after she'd been working for a while, so I went to her convocation. And at the arts convocation, they actually had Donald Knuth speaking. He had done some typography stuff. He also gave an organ recital at a church in the area too, so diverse talents. But anyway, so Donald Knuth developed TeX, this document formatting system, primarily for scientific type stuff, equation formatting, stuff like that. But he also developed fonts and all that. So anyway, TeX was kind of like low level, kind of like assembly programming. Leslie Lamport developed a bunch of macros around it that made it more user friendly. And so TeX became LaTeX, or LaTeX, which is used by a lot of people in the sciences for writing documents. So now the history is out of the way. Here's the scenario. We have three computers in our system, and they each have a clock, and they want to synchronize with each other to agree on the time. An example application of this might be in the aerospace industry, where you always have a redundant computer systems, flight control, that kind of stuff, and they will do the same calculations, and then they will output their result and agree on it. So one thing they have to agree on is what's the current time. So let's just say that we've got clock 1 at the top, clock 2 at the left there, and clock 3 on the right. And periodically what they will do is they will exchange with each other what the current time is. As you add more computers, this diagram, or more clocks, this diagram would become more complex and crowded. So we're just doing 3 here. So the idea is that we have n clocks in a distributed system use averaging to synchronize. So clock 1 tells clock 2 and 3 what time they think it is, and vice versa, and then they just each of them takes the average of all 3, and they have a new time. The problem is that a faulty clock can, well, obviously it can cause problems, so it can interfere. So let's just say, for example, that clock 1 is faulty. So clock 1 tells clock 2 that it thinks it's 0 o'clock. Clock 1 tells clock 3 that thinks that it is 3 o'clock. That's an example of something called a Byzantine failure, where a component can fail in an unreliable way, so it can prevent different systems to different observers. And we're going to talk about Byzantine failures later. That's something else that Leslie Lamport did pioneering work in. So now clock 1 thinks that it is 1 o'clock, and it faithfully tells the other clocks that, and clock 3 thinks that it is 2 o'clock. And if clock 2 and clock 3 were able to somehow exclude clock 1's values, they would arrive at a time of 1:30, which was the average of their values. But if each of them takes the average of those 3 times, so we don't care what time clock 1 thinks it is, because it's kaput, it's unreliable, it's doesn't matter. So clock 2 calculates an average, and this average is going to be the time from clock 1 plus the time from clock 2 plus the time from clock 3 over 3. So we end up with a time of 1. Clock 2 is going to calculate an average of 3, that's what clock 1 told it, plus 1 plus 2 over 3 gives 2 o'clock. And so clock 2 and clock 3 have not come any closer to agreeing on what the time is. So the moral of the story here is that averaging doesn't always work. And you could argue, what's the odds of clock 1 behaving that way? But when you do care about having a reliable system, then even if the odds are small, you do have to worry about it. So Leslie Lamport came up with the CNV, which stands for convergence algorithm. And the purpose here is to use kind of a modified averaging algorithm that somehow excludes the times from faulty clocks, and let the faulty clocks just think whatever they want to think the time is, but let the ones that are not faulty agree on what the time is and not be drawn away from the correct time by the faulty clock. So here's the algorithm. At time t, all clocks report their time, and we'll call that Cj. Each clock Ck, it records what it hears, so it records the time from each clock, but it does a little bit of filtering. So the time that it gets from clock J is recorded as either the time that clock J told it, if the difference between clock J's time and clock K's time, the one recording it, is less than some error-bound epsilon. If they are too far apart, then it replaces clock J's time with its own. Each clock Ck updates its time as, so the new time for clock K is going to be 1 over n for the sum of j equals 1 to n of the modified stored value. So for itself, it'll just use its own value. For the other clocks, it'll use their values unless they're too far apart from it, and then it'll substitute in its own time. That's the convergence algorithm.